Next attempt was CLAB color space. CIE 1976 color space, known as the CLAB system, is the result of mathematical transformations of the CLAB 1931 system. In order to differentiate from other systems, particularly the Hunter system, all CIE parameters are marked with a star, LAB, like that. You see the asterisk after the letters, that means CLAB. If not, it means Hunter Lab, officially, although you'll see the asterisk omitted a lot of the time. The object of this mathematical transformation was to obtain a space which is uniform in terms of color differences. That's what we're always after. Make the color differences that we see visually correlate with our numbers. To develop a much simpler system to interpret with easier references was also a goal of this newer system. Those are the equations that we've seen before. And again, the L, A, and B come from the tristimulus X, Y, and Z values. And it's a nonlinear transformation of those X, Y, and Z values. If you're interested in the math, I think Chapter 4 has a bunch of that math in there that's way beyond what we want to talk about. And I think in the very end of the book, there's an appendix with all the mathematical equations and all that kind of stuff. If you're really interested in that, you can look at that. But worry too much about that. As far as the math part of it, we've pretty much done that so far. What we did last week is really the only calculating we'll have to do. Mostly what we're talking about here is how do we use and interpret the numbers once we get them. Our CLAB color differences, color sensation described by hue, chroma, lightness, and darkness, like we've talked about before, arranged in an orderly color space, like a cylinder. Our hue is our closed circle. Chroma increases with distance from the center, and the height is the lightness. Picture there that we've seen and talked about before. Ideally, quality control technicians like to use one number to determine if a material passes or fails. That makes it the simplest. If you're measuring the size of a bolt, pretty simple. You measure it, and you have one number. Is it 5 inches plus or minus 1/10 of an inch? That's pretty simple. You just look at that one number, and it tells you whether it's good or not. Delta E is a single number that denotes total color difference that can and is used for making pass-fail decisions. So if you go in the industry, you'll find companies that use delta E as that number, pass or fail. You guys use that? Just regular delta E, right? So after today, you'll find out the problems with that, and you can go back to work and tell all of your engineers and quality control people that they don't know what they're talking about. Okay? You mean they wouldn't listen to you? The thing is, it's easy. You know, there's no subjectivity. You don't have to think. You know, and that's what they want. That's ideally the best thing. If you don't have to think to make a decision, that's a lot easier. The KISS principle, keep it simple, stupid, right? The simpler it is, the better it is. The question is delta E a good number for use as a single number tolerance? For you mathematical whizzes and experts, when we talk about CLAB color space, that space is Euclidean, and I'm sure you all know what that means from your math classes, right? Good. Glad I don't have to explain it to you. The important thing is that any distance within the space can be calculated as the square root of the sum of the squares of the component distances. We calculate delta E with this equation that we talked about before, and we've done this calculation, but that's why we square each of those values, add them up, and take the square root of that. That's how space is calculated in that type of space. Mathematically, that's a mathematical system. That's why we use this equation to calculate delta E. That's mathematically valid in a space like this. Just so you know, I'm sure you were concerned about that. We just didn't make this up. If we look at a standard in the sample, we can take our total delta E difference, like it says up there at the top. Delta EAB just means the difference between sample A and B. And we can take the component differences. Delta A, this one is that distance. Delta B is this distance here. Delta L, that distance there. we square each one and then add them up and take the square root of it. And that's the distance if we were to draw a straight line basically from one sample to the other and measured that. This was calibrated in inches. We could measure it with a ruler in inches. That distance would be the same number that comes out of that calculation. So let's look at the difference numbers a little more closely to see some inherent problems with using delta E as a single number tolerance to correlate with visual perception. The next slide plots two colors, A and B, in CLAB color space, like we've been doing. And since they are on the same line, originating from the center point, they both have the same hue. Well aware of that now, right? Chroma and lightness are the same for both. If we were to write the numbers, our delta A between these two is 2. Our delta B is 2. There's a 0 delta L. Our delta chroma is 2.8. There is no hue difference because we said they were the same hue. They're in the same line coming from the center. And our total difference is 2.8. All that difference comes from what attribute then? Lightness is 0 difference. Hue is 0 difference. So delta chroma is 2.8. Our total difference is 2.8. So all of the difference in this case comes from the chroma. So it would look like that. So we have the same hue, but different chroma. And the lightness is the same. Okay? So we could conceive of a couple samples that way, right? We could also another set of samples where the numbers are all the same. Our delta A is 2 again. Our delta B is 2. Our delta L is 0. But now, instead of all our differences being in the chroma, they're all in the hue direction. This time are the same distance from the center point. Therefore, they both have the same chroma. Chroma and lightness, that should be chroma and lightness, are the same for both. So this is what that would look like. But again, the delta E number is the same. Now all the differences is in terms of hue instead of in terms of chroma. If we look at the numbers, just at the numbers, we could conclude that the perceived visual difference between the two sets of samples would be the same. So if we looked at one set of samples and then looked at the other set of samples, we would say, no, those don't, both sets don't match, but the difference between the standard and the sample in both sets looks about the same difference. Okay, one's not way off and one's not real close, but they should look about the difference apart. Because for both sets, delta A is the same, delta B is the same, delta L is the same, and delta E is the same. Only the DH and the DC are different, but the magnitude of the difference is the same. According to the numbers, they should look the same difference apart. The problem is we don't see color that way. Okay? We see differences in hue much more easily than we see differences in lightness and darkness and chroma. So if we were to actually look at two sets of samples like that, what we would actually see is the set that has the different hue would look much farther apart than the set that had the difference in chroma. Because our eyes are more sensitive to hue differences than they are to chroma differences and lightness. But the equation doesn't do it that way. It gives equal weights to L, A, and B. So it doesn't include that actual and physical fact about our eyes is that we perceive hue differences easier than the other two. There is no weighting factors for the different axes, and they're all treated the same, so that can't be accounted for in the equation. The equation treats those two sets of samples we just talked about as the same. According to the numbers, the difference is the same between sample and standard number 1 and sample and standard number 2. But if we were to look at that, that's not what we would say visually about it. We would say that the samples that are different in hue look worse than the samples that look different in chroma. But the equation can't take that into account. Like I said, that's not how we perceive color differences. hue differences are visually perceived more easily than lightness or chroma differences. If all the color differences in one direction versus being evenly divided in all directions, it's also more easily for us to see the difference. All the difference was in the A direction, for instance, no difference in the B direction. That would look worse than if they were split 50-50 between A and B. All those kind of perceptual differences that our eyes have cannot be accounted for in the equation. So we talked back in the beginning of the class that we're trying to model how we actually perceive color by our equations, and we can see by this so far that it's not that great of a model. It doesn't account for all the things that are happening. To do that, it becomes much more complicated. A relative small numerical value in the hue direction will be much more visually unacceptable than a larger numerical difference in either the chroma or lightness direction. So we might be able to perceive a 0.2 difference in the hue direction, but it might take a 0.9 in the lightness or a 1.2 in the chroma. Again, the problem is the number doesn't always mean the same thing. So it makes it pretty hard to make a decision based on it. The equation cannot account for those discrepancies. Therefore, there are times when visually a color pair is judged acceptable, but the delta E is out of tolerance. Also, there are times when visually a color pair is judged unacceptable, but the DE falls within tolerance level. So it gives you the wrong decision. Visually, you say it matches. Numerically, you say it doesn't. Or visually, you say, no good, but the numbers say that it's okay. In either case, the number tolerance, the delta E, doesn't agree with visual evaluation. So if you're using that in the plant to make that decision, they're either throwing out parts that are good because they would be acceptable to the customer, but the numbers don't say that, or they're shipping parts that the customer doesn't want that the number says is okay. This demonstrates that there are some serious problems with using delta E as a single number tolerance. So what about breaking the total difference into its components and using those values for tolerance? So let's look at it more closely. Let's, instead of using one number where we see it doesn't really work very well, there's times when it doesn't agree, let's look at the individual LA and B numbers and see, maybe we can use that. It'll give us 3 numbers instead of 1, but maybe it'll be more accurate. First, let's look at the results of a similar experiment for CLAB color space that was discussed earlier with the color space defined by the chromaticity diagram. The diagram represents the plane of the A-B diagram. What we're doing is we're taking a sample and then adjusting it a little bit till we just see a perceivable difference. So like we did before, the ellipses on the next slide represent numerical values for matching colors. The center point is the target value, and the outer line represents the farthest acceptable match. Colors within the ellipse are acceptable match to the target value, outside are not. So we should have something that looks similar to the chromaticity diagram, and this is what we get. We end up with ellipses again. We don't get circles where it's uniform all the way around. We get these ellipses. If we look at them, we can see that, again, we have the same problem with nonlinearity. It's not quite as pronounced as it was in the chromaticity diagram, but this ellipse up here is much bigger than the ellipse down here. So in different parts of color space, we have that problem with the numbers being different sizes, meaning different things visually. And, depending on where we are in color space, those ellipses are in different directions. They're not all lined up the same way. If the CLAB formula would represent colors visually equal distance from the standard color in all directions, accurately they would lie on an A-B diagram as circles of equal size. That's not how it works. They are ellipses instead and tend to be aligned along radial lines from the center of the A-B diagram. Actually, they're aligned along lines of equal hue, pointing in a very specific directions that we'll explain a little later here. This causes problems when assigning color tolerances. Ellipses of equal size and shape result in widely obviously vary in tolerance terms for delta A and delta B, as illustrated in the next slide. It is also apparent that some of the resulting tolerance boxes exceed the corresponding tolerance ellipses substantially. Okay, if we look at this, what we can see here is that in different parts of color space, our A tolerance or our A acceptable differences and our B acceptable different sizes are different. So if we're up here at the top, we can be this far off in the B direction before it's unacceptable, that direction. But in the A direction, that's much shorter, much smaller number. If we look at this bottom one, it's the opposite. The A tolerance is much bigger than the B tolerance would be. If it's only off a little bit in the B direction, we can see it. If it's off that same amount in the A direction, it's acceptable. And then this middle one is kind of half and half, where A and B is about the same. So depending on where they fall in color space, the A and the B differences aren't the same. So that's not a good thing. From two previous figures, it is apparent that it makes more sense to set tolerances for lightness, hue, and chroma instead of using lightness A and B. You can use, instead of A value, a B value, and an L value, delta values for tolerancing, let's use L, C, and H. So we can look at it here. What that means is now we've had our, from the earlier slide, we have our standard and our sample. Instead of delta E being delta L, delta A, and delta B, it's now delta L, delta C, and delta H. Remember last time we said you can calculate delta E those two different ways, using LA and B or LC and H. You can see here on the bottom what the difference is. This is the chroma difference, the hue difference. Lightness difference is still the same as it was before. So we're breaking down that difference into hue and chroma instead of A and B. The difference is the same, but we're just breaking it down differently. So now if we look at this diagram similar to what we had before and look at it in terms of hue difference and chroma difference, what we see that this is much better. The chroma difference in all three of these different samples is about the same. The hue difference is about the same. So the hue difference is smaller for all of them. The chroma difference is bigger for all of them. That's better than the A and the B, where it depended where it fell in color space, which one was bigger and which one was smaller. So these don't change based on where they are in color space. So that's an improvement. So now all of the delta chroma tolerances are roughly the same size, and all the delta hue tolerances are roughly the same size, no matter where they lie in C-Lab space or which direction they are pointing, or which direction those ellipses are pointing. It looks like we're making some improvements. All those things are true, but unfortunately, that's not the whole story.